the framework themes, the Emergent Cognition topic. Our moderator for this session is Celia Merzbacher. Celia is Vice President for Innovative Partnerships with the Semiconductor Research Corporation and previously served as the Assistant Director for Technology R&D in the White House Office of Science and Technology Policy, where she supervised the National Nanotechnology Initiative. Celia has been Executive Director of the President's Council of Advisors on Science and Technology, so she's certainly familiar with the PCAST assessment, and was also a scientist at the Naval Research Laboratory. And she holds a number of patents for advanced optical materials. So let me turn it over to Celia.
Thank you, Chris. Thanks to the whole NCO staff and all the government people who are spending time here today listening to this group of fascinating people. My background is not in the field of networking and IT, but much more in the area of strategic planning, if you will. So when I speak, I certainly will focus on the how, and I think we'll hear from the rest of the panel as well on some of the how NITRD can achieve its goals. Our panel is Emergent Cognition. As Emergent Cognitions, we are to harness new levels of intelligence, intuition, and awareness, emerging as greater than the sum of the parts in the union of cyber, human, and social capabilities. So I kind of parsed this sentence, and I decided harness means use, and that new levels of intelligence, intuition, and awareness, well, intelligence, that's the brains, intuition is the guts, and awareness is your senses, all of them. And so you're using the sort of new strengths of these organs based on R&D at the union of cyber, which is sort of a physical sciences-based area, human or bio, and social. So our panel is going to really have a lot of latitude. You'll hear a lot of different views about how to take advantage of the capabilities that some of these technologies provide and how to do that. So with that, we will go to the first presenter, Mark Wegman. Mark is head of computer sciences at IBM with worldwide responsibilities in IBM's 8 research laboratories. His professional interests include programmer productivity, compiler technologies and programming languages, algorithm design, and information theory. Mark is a member of the IBM Academy of Technology and a fellow of the Association for Computing Machinery and has been designated an IBM Fellow, a high honor. And that is the organization's highest technical honor. So, Mark, 10 minutes.
Thank you. Just to start out, Celia did a good job of explaining what this panel is supposed to be talking about. We're not talking about, as Stu suggested, what happens in emergent cognition as you wake up in the morning. What we're talking about is how do you use information and to do something useful, and that might be to satisfy your curiosity. One of the things IBM looks at is we have a technology outlook where we try to prophesize the future, and one of the keys of that is what has changed that enables something new. And in my mind, one of the things we look at, certainly in IBM research, is what are the easy problems that are important that we can solve. It's better to find an easy problem than a hard problem if they're equally important. And the place that you see that is where there are changes in technology and there are places that are less combed over. So I think that there are some changes in society and technology that enable us to make decisions, to go from data to decisions, which is the theme that I'm going to talk about and is part of this general technology outlook that IBM is doing. That make it easier to do analysis and to extract information from data. One of those is simply there's a vast increase in the amount of data that we have available to us in a variety of different places. There's also cheap parallelism. So we can get a large number of computer cycles to analyze this vast amount of data in a way that we have not been able to in the past. So let me give some examples, which I'm not going to go over, but I assume that people are, to some extent, aware of. People have for a long time used computers to do optimization of processes. So you can imagine in the sense that we talk about smart planet, a whole pile of sensors all over the world, feeding information perhaps about the traffic in a city and scheduling the traffic lights so that you can save energy and get people through the city more rapidly. Another example is IBM is using the information we have about our service engagements, of which we have more than anybody else, to understand where we're not having the best quality, and as a result, we've been able to increase the quality of our service engagements dramatically, significantly increasing our profitability in those. And you can think about what that would mean in contexts like healthcare. So we've been for a long time using data to do decisions. And so what I want to do is very quickly take you through this picture here. What we do is there are various technologies for collecting data. You then want to extract the data. You want to understand it. So, for example, last night we saw the U.S. Constitution. If that was scanned in, we would still have to translate that into text, which is sort of extracting it, in order to do analysis of it. Then you enrich it by perhaps connecting that with other concepts on the web. And then you want to visualize it or analyze it in a variety of different ways. And that's sort of the technology foundation of data to decisions. And there are issues of how do you combine information. Let me just show you a couple of what I found, surprising examples that we've done in IBM. The first one I'll talk about is a system we call Many Eyes. And the reason Many Eyes is so named is that we want to get many people to look at data and to help annotate that data, to help analyze that data, to communicate about that data. And in order to do that, it's not sufficient that you simply collect all the data in one place. What we need to do is we need to build visualizations, and we've got some, I don't know whether they'd be comfortable with my saying that they're artists at visualization. We've got some people who built some beautiful, beautiful visualizations of data. And what they do is they put they allow anybody to upload data. They allow anybody to connect that data to a visualization of that data. And then they allow that visualization to be embedded someplace. So, for example, one group of people, somebody uploaded part of the Bible. And then they looked at a paragraph in the Bible and they said, this person exists in the same paragraph that that person does. And so they started building a social network of who knew whom in the Bible. What happened is that visualization was exciting to a bunch of people. They put it on the web. That got spread around to a bunch of different blogs. Finally, somebody said, oh, I could do that same thing with something else. And they went back to the Many Eyes site, and you get a cycle of people talking about data, annotating it, coming up with new realizations. I'm not a Bible scholar, so I'm not going to comment on the particular ones, but you get people talking about data in a way that we had not been able to before. And of course, as I said before, there's a lot of data available to look at. Oops, what is that? Oh, this is animated. I didn't know this was animated. It wasn't animated on my machine. I hope I didn't go past where I wanted. Here's another example. There was a group of people at IBM who wanted to build a system which answered natural language trivia questions. And I looked at this, and other people looked at this, and I said, completely hopeless. You cannot compete with good humans in terms of understanding natural language, understanding common sense, and answering, even simple trivia questions. So we have a group of 2,000 trivia questions. And by the way, this is work we've been doing in collaboration with universities, and I think that that's an important thing to say, that this is not just IBM that's been working on this. When this project started, which is where I first heard about it, we were at this bottom line there in terms of our ability to answer questions. And the reason that this is on a two-dimensional picture is if you try to answer every single question, you won't do as well as if you try to answer just the ones you're relatively sure of. And so that's why there's a line to talk about recall precision. And I thought it would take forever to get that line up any further. And then the group moved up to this line. And I said, oof, they were lucky. They did that in 6 months. Then the next line is another 6 months. And after a while, I decided that I'm not going to predict how well this group is doing because but you know, I'm not the only one. We've been able to do a very surprising amount of answering natural language queries. And the reason is we've got a large number of different data sources that just simply were not available a while ago. The other thing we've got is humongous amounts of computational power. These questions, you know, which a human can answer in seconds, if you tried answering on a machine like that, would take at best hours. So you know, it's not economically feasible now, but I think it can be. And you can imagine all sorts of uses for this kind of technology where you can answer questions by perhaps an expert where you get a lot of data about an expert domain. So that's just a sampling of things you can do with a large amount of data and a large amount of processing. And I think we really can push the boundaries by looking at different kinds of data than we've typically looked at, and finding surprisingly easy questions, surprisingly easy problems to solve that we had not been able to solve before. Just as a teaser, I think it's important to have a three-way cooperation here. When I talked about IBM working on the quality of its service engagements, IBM can do that better than anybody else because we have a lot more data than anybody else. Universities simply don't have access to that data unless they come through us. On the other hand, a university can take a much longer-term outlook than most industrial corporations. You know, if you look at the longevity of industrial research centers, there aren't a whole lot that are anything like as long as IBM Research. And I think that there's some real reasons that happens. So universities have an advantage that they can look out, but they need to look at the important problems. And I think that there is a tendency for a university to focus on problems that they understand. And so they don't reach out and find the important things that are not well understood. And I think that the government plays a role here in that I think it can grease the skids and make all this feasible, because I think without some amount of government initiative, we won't be able to get the two sides of universities and industry together to solve those problems. So I may have done, did I undershoot 10 minutes? No, right on the nose. So I guess now I get questions.
Yeah, a couple minutes for questions, right? Any questions for Mark? All right.
You made the comment that if there was an easy problem to solve and a hard problem to solve, it made more sense to work on the easy problem.
If they're equally important, if their solution is equally important.
I don't think I agree with that.
Okay.
Because I think if they're equally important, then you have to be willing to commit resources to work on the hard problem as well. Because otherwise, I really don't like the metric of just because something's difficult, we won't take it on because we could work on something else that is important that's easier. I mean, and just to give you an example, fixing math and science education K-12 is really, really hard, but
it's also really, really important.
Yes, but there are other really,
if you found similarly really, really hard problems that were a lot less important, it would not be worth investing in.
Right, but what I'm saying is there are other really, really important problems that are a lot easier to solve. I don't think we should only focus on them just because this one is so hard.
Let me say why I give that example. If you look at some of the results that I'm well known for, you probably know the work I did on universal hashing. There's a two-line proof. Now, granted, there's a lot of stuff around that, right? That's one of the things I'm best known for. It was harder than two lines sounds like, but it was only 2 lines. If it would not be possible now for a student looking at algorithms to find a problem that was anything like that important that had only a 2-line proof. They're all gone, which means that the students have to work on something really hard in order to find something equally important. I like that I did something important. I don't know that I could solve one of these problems which is equally important but is a whole lot harder. And so all I'm saying, I'm not saying that, look, there are fundamental problems that we should look at. I mean, I didn't mention that IBM is in fact working on biologically inspired computation, which I think could fit in this discipline, and is a fundamentally outstanding question, and I believe we should work on it. I'm not saying that when there are fundamentally important problems, we shouldn't look at them. But if there happen to be easy problems which are equally important, I'd rather put the money there. But when you talk about K through 12 education, there probably isn't anything of that order of magnitude that's left out there that's easy.
Just a question of terminology. When you are talking about industry, do you say information technology industry, or does this apply to scientists working directly with the end consumers of the IT, whoever it is? So if the answer is that it's both, then yes. If not,
I think that if you found a student who wanted to know what was important economically and wanted to work directly with, I mean, we're working directly with illiterate plumbers in India because they have interesting IT problems. And we need to do field studies in order to do that. And I think that that's fine, so long as the results that we produce end up feeding human knowledge. I think it's much easier, by and large, to go to an IT organization that understands the fundamental problems for a university and to make progress in something that will be publishable and which will feed the human knowledge. But I do believe that at least some of the times, and there's certainly Citrix, for example, is a group which is working directly with customers by some definition. And I think we need to do that as well.
So when you, I'm just trying to understand your views on the government helping universities to create open source solutions that are going directly to the end consumer and bypassing the IT industry.
I think that that's great, but I also think that the universities should be working with the IT industry as well, because the IT industry has been able often to boil down an important economic need in a way that universities are often unfamiliar with. And so there's a collection of problems out there which are missed because they fit between these two camps. And I think that beep was mine. But we can
That's a good place to stop or pause. We're obviously going to revisit a lot of these ideas during the panel discussion. Okay. Get Tom up here. Okay, our next panelist is Tom Baer. Tom is the executive director of the Stanford Photonics Research Center and a member of the university's Applied Physics Department. His research spans many areas of biotechnology, laser development, and laser applications, and he's listed as an inventor on over 60 patents. Tom is the 2009 president of the Optical Society of America. Thank you for that volunteer work. And as founder of the Arcturus Bioscience, he received the Silicon Valley Business Journal Entrepreneurial Award for Emerging Companies in 2000. Tom.
Thank you, Celia. I'd like to thank Chris Greer and Sita Furlani for inviting me to be a part of this, and especially Celia as well for organizing a pre-conference telephone call in which Mark Wegman and I discovered that we had a lot of common things we wanted to say, so I've shamelessly stolen one of his slogans, which is Data Decisions. And we're going to be discussing part two of this particular concept of what is, in particular, what I'm interested in is explaining what we've developed as an infrastructure to support the efficient progress towards making intelligence decisions based on an explosion of data that's now available. This is a commonly shown picture of the structure of the Internet, which shows the amazing complexity that it currently has. It addresses 25% of the world population. There are about 250,000 different IP addresses, and it's growing exponentially. Not only are the number of users growing exponentially, but the data per each node in this graph is actually growing exponentially as well. So the question is, given this large increase in data, how do we discover the valid information that's necessary to make educated decisions? I'm going to give two very different approaches towards building an infrastructure to address this challenge. Another interesting question is, given this, the growth of the Internet today, how is it growing? And I would suggest it's growing primarily in response to supply and demand, in that where there is a demand for bandwidth, the market responds by building capacity. That's a very valid way for the market to grow or for the Internet to grow, but an interesting question is, given the increase in data, is this the best way for the Internet to expand? The original intent of the founders of the Internet was to create a framework for the efficient exchange of information between a small number of federally funded research facilities. It is interesting to note that because they selected the people that would be on the Internet, there was built-in quality control. For the past 100 years or so, the Optical Society of America has been involved with disseminating scientific information and had a very similar mission to take high-quality information, disseminate it amongst its community of researchers. Over the past 4 years, I've been working with the OSA to develop what we call interactive scientific publishing, which expands the notion of what scientific publishing is all about from text-based manuscripts to include source data, dramatically increasing the amount of information that's available to our community of scientists, increasing it by many orders of magnitude. So I thought I'd start by discussing a little bit about the origin of scientific publishing and peer review. It started in 1650. Henry Oldenburg was the secretary of the Royal Society back then, and he worked with a number of very famous scientists. And this group of scientists within the Royal Society was exchanging letters amongst themselves, describing their scientific observations and results. They asked him to coordinate this exchange of letters, so instead of them copying it and sending it out to everybody, they sent their letters to him, he would copy it, and also act as a first-order screen to determine that it was appropriate to be disseminated to the members of the Royal Society. This was really the first example of peer review, and essentially this is the way it's been, scientific publishing has been for the last 300 to 350 years. This is indicated here, which shows how this information was exchanged basically over this evolving time period. If you assume, it's interesting to calculate what is the baud rate for the transmission of this information. If you assume that 30 articles is a typical journal issue and that each article is about a megabyte at high resolution, again, these are text-based with a couple of figures in it, then the dissemination would take a couple weeks and is about 30 baud for a typical, it's 30 megabytes of information. As you go through time, you'll see that though the transportation increased, speed increased, the actual transmission rate did not increase significantly as we went through this time period. And in fact, one of the major bottlenecks was the last mile. So this has been a bottleneck for hundreds of years, not just with the recent telecommunication infrastructure that we've put in place. It's also interesting to note that in this time period here, that we could transmit by fax, given the slow, about 600, 1,000 baud rate of the fax, it was much more efficient just to ship the journals in, and distribute them by the post. What really changed was about 10 years ago with the introduction of the Internet, where all of a sudden we saw 3 orders of magnitude increase in bandwidth. So this has been a major change and allows us to really extend the capacity and the amount of information we can distribute quickly to our scientific community. Why is this important? Here's an example. This is a figure that would appear in a normal radiology journal, for example, and it's a picture of a lung cancer tumor. It's a two-dimensional image, and this is very typical of what you'd see as a case example of lung cancer case. Here is an example of what is now available to our community of users when they download the appropriate viewing software, and we supply the full three-dimensional data set. That previous image was about 100 kilobytes of data. This is about a gigabyte of data. So it shows you what is now available in terms of the different views that you can see. And it also shows you that the user can interact with this data and manipulate it and do quantitative analysis on the data. So it is a remarkable increase in the capacity to be able to understand and evaluate the scientific data. This is of critical importance in this area. Here's an example of a CT rendition of a three-dimensional CT data set. And using the software, you can also extract volumetric information, which is important for drug response and for screening capabilities, as well as other aspects of the different nodules that would be present. Again, you just can't do this. You don't have this interactivity that's associated with just a two-dimensional view or JPEG image of the data set. So this is the type of capability we are enabling. What does it take to do this? Well, it takes some key characteristics. And I think these are general characteristics for anybody that wants to really go from, again, data to intelligent decisions. You need to have a permanent archive if you're going to be part of a scientific publishing enterprise. You need to establish standard data set formats. There needs to be not only the data, but also metadata in standard metadata terms. There needs to be quality control of the data, and that's part of the peer review process and of the metadata. And then there needs to be infrastructure in place for a metadata search tool. We've also been proposing and developing an open source software platform similar to what Mark was describing, which provide visualization, feature extraction, quantitative analysis. And again, part of the publication process will be submitting software and plugins for this software platform. So this is the way we see that scientific publishing is going at this point, is towards supplying this kind of infrastructure and to support the data sets that are there. You know, as I was saying before, the market, as I see, the internet is growing primarily in response to the forces of supply and demand. It's interesting to consider what other ways you might actually grow this internet rather than through this sort of evolutionary pressure. And so the rest of this talk is inspired by some of the work I've been doing in neuroscience, where there are other types of networks. This is the dendritic tree from a Drosophila fruit fly, and this is part of the work I've been working on at Stanford. And it shows a different type of network and the capabilities we have now for mapping out the nodes and interconnectivity in this particular type of network. This network has evolved through evolutionary pressure. It's basically for survival. And the network itself is designed to facilitate and speed the processing of the data. So it actually involves in the process of taking data, in this case from the sensory organs of the eyes of the fruit fly, the pattern recognition takes place within the network itself, and then those patterns are what is transmitted to the actual decision-making apparatus within the brain of the fruit fly. So these are green fluorescent protein labeled single neurons and axons, and then that indicate the computational machinery. This is the sort of thing we can do in terms of mapping out the structure of living animals. These animals are alive. We can watch not only and determine the morphology and structure, but we can actually now watch the neurons fire and in response to visual stimuli. So fairly soon, within the next 5 years, these network structures, these computer structures will be completely mapped out, and I think we will be able to follow the information flow. And this may be an inspiration for the next generation, how we would design our own network. Here's an example. The fruit flies again, are hardwired to respond to visual stimuli in specific ways. The patterns are sent to the brain with predigestion of the data. In this particular case, it illustrates how we are pre-wired. If you look at this closely, you'll see gray dots at the corners of the squares. And that is because we have similar sort of pattern recognition. In this particular case, these lines are all parallel to one another, but they look like they're slanted. And this is because we have similar sort of built-in information processing that takes place within the network itself, which helps us quickly process information. In the case of a fruit fly, it wants to know, is it food or is it a foe? Should I jump and fly away, or should I eat it? And these are the sorts of things the fruit fly needs to make decisions on. They're life and death decisions. It needs to make these decisions very quickly. And the structure of its network is designed to process the information effectively and provide a much more efficient way to go from data to decisions. So just in conclusion, the structure of our internet is now growing on the basis of, again, basically supply and demand. Is it the role of NITRD, perhaps, to look at different ways that we can structure the internet in its growth to better and more efficiently process data and make intelligent decisions? The first example I showed used the infrastructure internet and was kind of a neutral approach towards the data. The second shows a bias towards providing relevant information to the decision-making process. Is this something we should try to do and emulate? Should we try to emulate nature in how we encourage the evolution of the internet? And that's a question I kind of throw open to the audience here. So with that, I'll close.
We have time for one or two questions.
I would like to enhance the.
Make sure to use the mic.
Sorry. Jung Lee from University of Iowa. I'm a faculty in the radiology department. And I would like to enhance Tom's talk about imaging data in health science. And recently, the whole radiology and medical school moving into the direction of called digital medicines. And they emphasize that into the telemedicines and teleradiology. So most of the data to fighting for cancers are currently are moving from the couple meg to a gig meg for each visit. So most of the case being realized emergently need to diagnostic cancers because of the for example, like ultrasounds, for each visit they can only handle for very small sections of clinic data. But when the case become more complicated and they have to pulling all of the data back to see what is a complete visit data. But on the other hand, whole United States capacity is not enough to handle this. So that's what the whole medical community are crying about this. So before this meeting, I had a ISNA meeting, and then they asked, is it possible to deliver a message to the community in this IT to see how we can find a solution for this. And that is what the really big demands for using the future internet to solve problems. Now, currently, the curriculums to teaching this, it's called medical imaging informatics or radiology informatics. And most of the courses from the beginning to the end are completely in computer science IT infrastructure offered to the medical radiologists, medical students. So that is what I would like to emphasize the importance of this, to see that this community can come up with some of really concrete solutions to help the increase or enhance the healthcare in the United States.
It's more of a comment. If we can keep the questions directed on the talk, and then we're going to have a lot of time, this is a good point to come back to. Thanks.
I wanted to comment about your comment about whether we should or could influence the evolution of the internet. I think it's actually not a well-formed question, because the internet, to many people, is sort of what they can touch and kick. I mean, people tend to think of it as the collection of lines and routers and switches and computers. I have a very different view of the internet. I think it's codified in the Federal Networking Council's definition of it way back when, which is that the internet is, in fact, a global information system that consists of sets of protocols and procedures and methods and defined formats that enable information to be passed back and forth between nets, so that information from a machine on one net can communicate with a machine on another net without the user having to know all the details of it. If you take that notion of the internet, then the question of whether it can evolve or not breaks into two different pieces. The part that you are, I think, alluding to is the fact that there is an underlying architecture to the internet that's very hard to change. It can be changed at the margins. That's something I plan to talk about tomorrow. But in terms of what people do, that's the same question as what do people do in society. And can you change that? Should you change that? You know, it's what people do. In the marketplace, they do what they do, and the net effect is what it is. But you can change the rules. You can change the procedures. So I would say the question doesn't really make any sense if you're talking about the protocols and procedures, because that has been evolving, it has been managed, it has been structured from day one. And if you're talking about the actual deployment of the internet, that's a very different question, and it's really the result of a lot of different choices made by a lot of different people.
Well, of course, if anybody can talk about the internet, it's you. I was talking more about the latter, and the way I was seeing the structure of the internet being determined by market forces with more bandwidth. What is the bandwidth of a communication channel to a node of data? And should that bandwidth be determined by the quality and relevance of the data? so that people can access data that has a certain importance to it and a certain quality level to it more effectively, like the fruit fly does. It pre-processes the data in order to be able to make the most intelligent decisions. And should some entity be involved with determining who has the widest bandwidth to supply data to support those decisions. Right now it's market forces, and I suggest that those forces do influence the bandwidth and what information gets delivered first. And if we let the market forces do it, there are consequences. It's not neutral now, and should we intelligently put in place pattern recognition and other aspects, at least we understand, which will allow us to get data of a known quality and relevance more quickly to the user. But we can talk about this further.
This is a big topic. It gets pretty political pretty quickly. Falia is our next speaker. Thanks, Tom. Falia Macadon is the Jenkins Garrett Professor and Chair of the Department of Computer Science and Engineering within the College of Engineering at the University of Texas at Arlington. Previously, she was Professor of Computer Science at Dartmouth College, where she founded and directed the Dartmouth Experimental Visualization Lab. Falia is currently Director of the Human-Centered Laboratory that studies human monitoring and develops pervasive technologies and privacy and security algorithms.
Yes, thank you very much. My talk follows very much the first panel, which was excellent, and also the presentations of Mark and Tom. I'm approaching the concept of emergent cognition bottom up, from the teacher-researcher perspective in academia, and looking at emergent cognition arising from applications and real-world challenges, especially having to do with healthcare. So I'm asking what types of federal investments can best be put into the service of human condition, improve productivity, as we were talking about, competitiveness, enhanced training, and my focus, improve healthcare and safety, both at home and at work. So the first slide shows an example of emergent cognition in a recent NSF thrust that can be described as cyber-physical systems, where we have a connection between the physical and the digital worlds and seamlessly, and basically collecting seemingly unimportant data and converting low-level data, like Mark was talking about, to meaningful guidance and recommendations. And of course, networking is very important in this case. So data collection and networking are important partners. So I focus on work that we've been doing on assistive cyber-physical systems, in other words, enhance the daily performance of the human. This figure on the left, upper left, is really the logo of our lab, the Heraclea Human-Centered Lab, and it's basically symbolic. It basically shows a physical environment that it was an ancient city where it's now East Turkey, and it shows a broken physical environment that doesn't make sense. It's certainly not functional for a human. It has columns that are broken, reaching out, and the question is then, what kind of cyber infrastructure one can develop and what kind of tools to make something like this, a physical environment, functional and helpful. Bottom left shows the actual apartment we have in the Human-Centered Computing Lab, which has bedroom, kitchen, and all that, and over $2 million worth of equipment, thanks to the state of Texas, with Vicon cameras, robots, and so forth. And all around them are researchers and also faculty who share the facility, who we are trying to develop algorithms of different sorts in order to gain meaning that would guide different tasks. So in this case, we're applying computational thinking into and abstracting it. As you can see on the right bottom, this is because computational thinking without abstraction does not make sense, and this is a way where the right bottom figure shows very different types of sensors, RFID, and we're also working with people at the University of Maryland on nanosensors that will be beacons for regular sensors to detect noxious gases and so forth. And on the top right is basically our wish list of this being a human-centered and assistive environment, both at home and at work. that provides intelligent data processing, meshing highly heterogeneous data, able to recognize what we call events, and these are defined accordingly, as I'll talk about later. Provide alerts, predictions. It's non-intrusive and secure, intrusive only when it's needed, and we're working with a nursing school on identifying what type of data is sensitive, when is it sensitive, when it connects with what data becomes sensitive, and so forth, and that it is on-demand, secure. And so we're working with people at UC Davis, Matt Bishop, on defining a framework for privacy and security in such a pervasive environment. And also there are a lot of interns that are involved, undergraduates and also high school students, where we immerse them into new modes of learning. It's just the opposite, basically starting from the lab and using the papers and the library and the classes as a reference in order to solve a particular problem, program a particular bioloid to do a certain task, and so forth. So let's go to the next one. This is an example of what we mean as an event. There is a whole series of animated slides, but here, what do we have? We have a space where the stove is on, and the occupant is in the closet. And so depending on the metrics, you know, how much time passes by, what is heat, and so forth, one identifies an event, and then there's a sequence of events too, and episodes that take place. And this can become a reference for the system to learn and predict and identify new events. I think we've heard this before. The issue here is that it is quite a challenge, really, to implement, oops, I have to go backwards. Sorry, to implement such a system. Not everybody is fortunate to have the kind of infrastructure we have there, or the funds. So it is very important for this kind of empirical research to derive also valuable data sets that can be sanitized or that can be searched, and that's what we're doing in a digital library of assistive cyber-physical systems. I want to make sure that I cover all the comments, but of course, you know, I never. So to recognize events is a very complex situation. This is what this slide shows, the realization of such a pervasive, complex environment where we have software and hardware components interacting with humans in a loop, a feedback learning loop, and we have caregivers, emergency people, physicians, and so forth interact. So the big issue here is developing software, new types of software that really can put a system together. Right now, most such systems exist in industry or in small senior design projects that are really pet projects. My claim is that it is important to start from year one in college, to be immersed in such things, to motivate learning and theory, and understand why databases are important and why security and privacy is important. And understand, and then by working like what new ways are there to collect data. This is how to identify catastrophic and costly health accidents. And all this modeling is very compelling, and I believe that undergraduates that we have in the lab are fascinated because they see how they can prevent falls for their grandmother or improve the energy of their homes by looking at our environmental sensors. So I also want to repeat the statement I made before that it is very important that the federal funding goes into building facility cyber infrastructure of this form and be equally important as to the supercomputing facility funding that goes. And I think they're both very, very important. And interdisciplinary team building, as we talked about before, is also very important because the time has come for computer science that we have to reach out. We cannot invent problems and then invent solutions to the invented problems and publish them and get tenure. This is not good for the nation. And I think what Maria Clava said about, well, let's put incentives in there for research funding that also would work for tenure, to support such empirical, high-end environmental infrastructures that will be part of learning and research. So the final slide is basically a recap. The challenges and impact of emergent cognition. Basically what you see on the right, that there are different factors in building such complex environments, in our case assistive environments: functionality, security, cost, architecture, usability. And the way we approach it is with a lot of interaction with industry. Somehow the Dallas Morning News did an article on us, and I don't know how, and then suddenly it was like 30 newspapers around the world, and then there were so many Dallas area companies that wanted to come. They're actually doing it. They're not worried about performance, scalability, security. They're doing it. They want to build companies that monitor 200 homes at the same time. And so this brought us closer to them to understand usability, to understand cost, to understand things like this, and that's important. And of course, there are the technical challenges of algorithmic complexity, privacy and security, where if you don't have secure networks and people can basically jam your networks, then the system is not robust. And you can't talk about any monitoring environments without ensuring privacy at some level, even though research has shown that the elderly at least, are willing to give up some of that for safety. And of course, building user interface, like Mark was talking about. We are building an information visualization space that basically summarizes about a given event what is critical and what's not critical. And this is such a great environment for innovation, working with industry to build new devices. We're working on the Smart Cane project and developing evaluation metrics. And I want to close by saying two concrete things we're doing. We got funding from NSF for doctoral consortia in a conference called PETRA, Pervasive Technologies Related to Assistive Environments. We did it last year, and we're doing it again this year. And also we are spearheading, it's almost ready to go out, an undergraduate research journal that's all electronic, and basically will provide incentives for students to publish their research. Thank you.
Thanks. Great. Thank you very much. We have time for a couple questions. Assistive technology is really, I think, a great application driver for emergent cognition. Maria.
I just want to make the comment that areas like assistive technology are one of the areas that really attract women and minorities, because they can see why it matters and how you can make a difference to society. And any time I've had a project working in assistive technologies, right now we're doing one on Dance Revolution for the elderly to increase aerobic capacity and mobility. And the entire team is female, which I didn't realize until one of our students commented that was the first time she'd ever been on a project that was all female in computer science. Also, when we did the aphasia project, in terms of always more of the students were female than male, often almost all of the students. So, you know, as well as being a very important application, emphasizing this kind of research and making it accessible to young students is a great way to bring them into the field.
Thank you. In fact, I just wanted to add to Maria, you know, some of my foreign students, the advanced, PhD students and postdocs, at first, when I told them that after 17 years of doing algorithms in brain imaging with Dartmouth Medical School, we will go into behavioral biomarkers and do this, they said, this counts for research? This is going to be research? I said, yes, because look at all the algorithms we have to put together and stitch them into something that makes sense. And then they shut up. Yeah.
So my comment is that emergent cognition often leads to emergent behavior. So how do you control the actuators and the agents in your environment? Because that's where you're going to have your impact. And if you have these emergent behaviors that you don't really understand, you could get yourself into a lot of
trouble. Well, we're in cave age at this point doing that. We set up, I've been there 2 years. So we set up the lab, and through sensors and also programmed expert knowledge within we build it case by case, working with a nursing school. Like, first of all, validating the fact that they went from the bed to the bathroom during this time following this path. That is a hard problem, believe me. And to do it without video cameras, because you don't want invasive things like this. We only use the video to validate the algorithm. Yes, what we saw with the Vicon cameras is really what happened in this amount of time. So yes, this is a very challenging. That's what we're doing.
So our next speaker is Mike Nelson. Mike currently holds the position of Visiting Professor of Internet Studies in Georgetown University's Communication, Culture, and Technology program. Before joining the Georgetown faculty, he was Director of Internet Technology and Strategy at IBM, where he worked with university researchers on the development of next-generation Internet platforms. Michael was also Director of the Technology Policy at the Federal Communications Commission and served in the Office of Science and Technology Policy during the Clinton administration. Mike.
Well, thank you very much. I'm very glad to be here and very glad that NITRD is doing this process. I think this is incredibly important, both to define for themselves where they're going and what they want to do, but also to explain to the outside world and the agencies that fund this effort why it's important. I also want to particularly thank Chris and Jean and Jeanette, and Sita for inviting me to be here. I have a somewhat different background, as you just heard, and I think it's a sign that we are really looking for a multidisciplinary approach, that you have somebody who is a geophysicist by training who spent 10 years in government and time in industry working on policy issues to talk in this forum. Though I have to say I'm not happy to be in this time slot. This is the time slot when the carbohydrates from lunch kick in. I just followed 3 outstanding speakers, and I now have to come up with something better to say. And everybody has sort of a buffer overload because they've heard so much information so far. But I'll try to make it provocative and try to be exploring things we haven't already explored. So let me start by giving you just this is my bio. As I said, I've spent 10 years in government, 10 years in industry, and now I'm in academia. So I've seen these issues from a lot of different sides. Let me now share with you the most important thing I've learned in 20 years in Washington. Those of you who've seen me talk before know that this is one of my favorite slides. This is what you need to have in Washington. You always have to have a good bumper sticker. So I'm going to give you a few bumper stickers about where I think NITRD can go. And I'm also going to talk about how NITRD can come up with some good bumper stickers, because I think we do have to explain what this is all about in some very clear language. And I commend the planning team for getting 2 of the 4 bumper stickers right so far. Trust and confidence, that's something everybody understands. And it really does summarize a big problem. Cyber capable is a great bumper sticker. It's a great buzzword, very effective. Emergent cognition does not work.
Can't think yet.
Yes, exactly. Can't think yet. I would propose something like the global mind or the global brain, something that gets to the sense that we have this distributed thinking apparatus that we're building, combining people and systems. No, you only get four or 5 syllables is all you get for a good buzzword, okay? Iron Curtain is a great buzzword. Strategic Defense Initiative. That was a really bad buzzword, because the next day it became Star Wars. So if you don't come up with a good buzzword, they come up with one for you. Even worse than emergent cognition is beyond virtual. When I was at the White House and I talked about virtual worlds and virtual machines, the reaction I got was, virtual? That means it doesn't exist. Why are we funding this? Beyond virtual sounds like something that you should certainly not fund. So maybe beyond simulation, let's think a little harder about bumper stickers. But anyway, so always have a good bumper sticker. Let me share with you a few bumper stickers. First off, I have a longer talk called 50 Things I Learned in Washington. This is an after-dinner talk. 50 bumper stickers I learned. Lesson 18 is, when in doubt, think like a user. Think like a typical user. And in our case, or non-user. And we haven't had much talk about that. I think part of my goal in this 10-minute talk is to get us to focus on the people who aren't being served yet by the research that goes on in NITRD. When I was first involved in the precursor to this program 20 years ago, it was all about leading-edge technology for leading-edge users. And we still have a lot of those people who have very big problems and still need answers. But we also have an opportunity to use the tools that are coming out of this program to meet the needs of the lagging edge, the people who aren't online. One of the most interesting assignments I have is that I'm on the advisory board to the Pew Internet and American Life project. And they do these surveys of Americans by telephone asking them how they use the internet. And they keep finding that there's a core group, 10 or 20% of Americans, who just don't see any use for the internet. They haven't found a way to make it part of their life yet. And you ask Joe Sixpack what they care about, number one is jobs. And we all understand that this program can help there. But when you ask them about IT, there's lots of different concerns. And some of the research we're talking about can address those concerns. Cost, security, and privacy, those are important. We're going to talk about security and privacy tomorrow. But they're also worried about the complexity of the system, the fact that they feel that information overload. The thing that we get most when you ask the average person whether they need to get on the internet is, and the average non-user, what you get most is, I've already got the information I need, I don't need Facebook, I got enough friends already, I've got all this information coming at me and I can't sort through what I got. So why are you going to give me 10 times or 100 times more? And then they worry about veracity of the information that they find on the internet. So these last three issues are ones that this panel can talk a lot about, I think. We can find ways to build the tools to tie all these people and information together with systems that will help make the information more useful and turn that information into something that actually solves problems for people. For Joe Sixpack. And we're not just talking about Google apps to help them find a Chinese restaurant. We're talking about a whole range of issues that they need help with, and we need to think about that user as one of our test cases. George Gilder has done a great job of bringing home just how big the flood is, how much information is coming at us. He talks about the exaflood. We all know these numbers are completely bogus, certainly wrong by a factor of 2, one way or the other, perhaps a factor of 5. But we're looking at a factor of 50 to 100 increase in the amount of bits available on the internet in the next 6 or 7 years. And that data is from all sorts of places. Movie downloads, video conferencing, cloud computing, television delivered over the internet. All we know is that there's a lot more data coming at us, and we've got to get better tools that use the power of machines and the power of people to sort through it and find what people need. Social networks are going to be part of this, and understanding better how social networks allow people to talk to each other, share information, share insights, analyze information as a group is really important, and that's a fundamentally multidisciplinary issue. Clay Shirky has a great book. I hope most of you have heard of the book, and I hope most of you have read it. It's called Here Comes Everybody, talking about all these ways in which online networks are allowing the sum of the whole to be more powerful and more intelligent than the individual parts. Just to finish with one diagram here, we've got this pace of technology. The hardware is always out front. Every few months there's a faster chip, a faster disk drive. Then we create the software to make that useful. This program, in the early years, focused on those two pieces. We've got to spend more time on the people piece, the wetware, making sure those people are comfortable with the technology and that the organizations they're part of are aligned to really take advantage of these tools. The problem right now is the gap's getting bigger. The gap between the technology and the people is growing because we haven't thought about people enough as we've designed the technology. And we haven't done the studies to understand how people react to the technology and how organizations have to be redone. So with the final slide here with some challenges, these are really about how, not about what NITRD needs to do. Again, top of the list, Keep the typical user and the non-user in mind. Think of the case studies that aren't just about astrophysicists and nuclear weapons designers. We've got to understand how people, systems, and networks mix together, and part of that means that we have to do a better job of collecting data on how these systems work. So when someone comes in with a great proposal for a new architecture, there should be 10% or 5% included for data collection on how that system is working. It may not be their focus. They might not really care about how users are using the network. They just want to see where the bits are going. But collecting that data might be the key to 10 other really exciting projects that will enable us to understand better the human element, the user element in that system. We also have to do some sociology, psychology, understand users' motivations. What causes them to share information online? What causes them to put the time in to do a Wikipedia entry? Things like that are important if we're building this global brain that consists of all this content analyzed by all these millions of people. We've already talked a lot about fostering multidisciplinary work, and I could, during the discussion, I'll talk a little bit about some things that Ben Schneiderman and others at the University of Maryland are doing to look at how these systems, how these cognitive systems of people, data, and computers can help us solve fundamental problems in public health, libraries, and the like. And then the last aside, this is really a footnote. Several people have mentioned it already. We've got to do a better job of making sure that these wonderful prototypes that are coming out of universities and laboratories are robust enough that they're used by other people than the PIs, and that commercial players can pick them up and start using them throughout the economy. So thank you very much.
Time for questions.
What is the
mic,
difference?
The mic for the people on the web.
Sorry. What is your paradigm of the major difference between the period of time when you helped to design the information technology for the cabinet of the Albert Gore during the Clinton's period and today's period of time? What is the major difference? Just key difference if you want to design this.
I think the biggest difference that I've seen since 1990, which is when we passed the original legislation, and now, is just the growing community of people who are working on computational research as opposed to computer research. And I think there is this broader community that's starting to understand how to apply these tools in hundreds of different disciplines. So I think that's one big change, and it's been a tension throughout the whole program. We've had this tension between the computer scientists who want to solve fundamental computer science problems and the biologists and the cosmologists and the environmental modelers who want to take the tools, modify them, and apply them to their own problems. That's always been a tension, and we continue to see that. I think the other big difference, and this is a healthy, very healthy development, is that we do have more people trying to span fields. When I first got involved in this, not only was it very much focused on computer science, you had people within their subsegment of computer science who didn't really want to talk to people in other subsegments. So the algorithm people were busy working on their problem, and the hardware people were over there, and the network people were over there, and there wasn't as much discussion as we see today. So that's I think the biggest difference. The other big difference is some of the most talented people from the universities in the mid-90s all went off to the private sector, and we not all the talented people, but there was a huge brain drain as we saw a change in focus. We lost some years there where we, instead of having the leading work, a lot of the top flight work being done in the universities, 90% of these students were going out the door and going to work at startups, and as a result, we didn't have quite as many new people bringing new ideas into the academy. That's clearly shifting back now. Those are just some observations.
I'm sorry, this is important.
Yeah.
So do you think that if we designed a national strategy which can help to leverage the level of internet to create more jobs for the states, or just like compare with the Clinton period of time, because it's IT blooming period of time, Do you think that is something we can consider? Or I mean,
I think it's inevitable. I mean, what we've seen is this boom bust. We had the internet bubble, which drove a lot of job development. When I was at the White House, we were boasting all the time about how many jobs were being created in the IT industry, and then we saw the collapse in the early, 5 or 6 years ago. The nice thing about that collapse was that unemployed software engineers went out and created Web 2.0 and laid the foundation for the next round of innovation. And I think we're going to see some of that now. If we put in place the environment that enables these people to play when they're in university and develop new ideas, I think that's the key. We also have to fix our venture capital system, which that's something a lot of people in this town are working on.
Susan Gray in Berkeley. Is this on?
Yeah.
I have to
Closer.
I have to disagree with your last bullet because I think there you've got the what correct and the how wrong.
Okay.
Having been involved in the creation of a lot of research prototypes, they're not created to be robust software, and in fact, the more exploratory they are, the less robust they are. That's not the purpose for which they're built. They're built by students with relatively little experience, and to take those artifacts and try to commercialize them causes all kinds of problems.
Yeah. I think you misunderstand my bullet. I was not saying that the students and the professors who develop the prototypes are supposed to go and turn it into commercial software. My point is you've got these really powerful ideas implemented in code, and often they fall flat on the floor. They don't go anywhere. I do think that there's an opportunity there. There's a chasm that needs to be crossed. I think that software can often get a lot better, a lot faster, if it's at least robust enough to be used in 5 or 10 or 25 other university projects, at which point some other company comes in and says, hey, we better look into this. But I think what maybe not clear on this is that the prototype and the software and the commercialization are done by different people. But we have to make it possible for the technology to move faster. Often the best way is to hire the students and let them do it. But it's not happening now.
One more.
Myron?
Yeah, it's something that related to the increase in the number of users and the size of the problems, right? I think one of the things that have changed is that in the old days, if you came up with a queuing model for a machine, you were able to go to the basement and try it out. Mm-hmm. And because it was self-contained. Today, if you want to try something out on the internet or a distributed system or whatever, very few, if any, have access to the experimental setting of this. And we heard earlier from IBM is, okay, we have the data, we can give it access to you. So I don't know if you have any thoughts about how we are going to deal with it, because an organization like Google have access to a tremendous experimental environment, right? If they change something, they can try it out right away and figure out what's going on. And for us, I would argue, on the scientific side, the only place we can go is to the scientists around us. And they provide us with significant data and with challenging problems, but then we have to create production quality software to get them engaged, because otherwise it doesn't work. So there is, I don't know whether you have any thoughts about how we deal with it, because it's very difficult to have breakthroughs in computer science without trying it out.
Yeah. Well, I do think the development of things like Amazon's Elastic Compute Cloud is one part of the solution. If there's a way to make some of those cycles available, perhaps Amazon can start donating more of those cycles as a way to get the academic community on board. But I take your point. There's certain types of problems where it's 100 times easier to do them today than it was 15 years ago, because cycles are so much cheaper. But the really exciting problems are these distributed systems problems that involve multiple institutions and large networks, and we don't have a playground for doing that. And so that's part of the thing that I hope NITRD will look at. But The good news is we have no shortage of problems.
Yeah, just one comment is, and you pointed out the user perspective, is having the playground is the easy part. Having engaged users that can tell you what's right and wrong, that's what Google has, right? If they change something in the search strategy, they have 1 million hits in the next minute and they figure out what happened.
I'm going to cut it off. There's obviously a lot of interest in this, but we're just a few minutes behind, and I want to keep us on schedule as much as possible. But we'll be coming back to all this, of course, during the session that follows the break. I chose not to have any slides because I figured going last, everyone else on the panel would probably say a lot of the things I wanted to say, and so I just made a few notes that I'll cover here without benefit of any visual aids. When I thought about this issue, many of the thoughts that I had were really not specific to emergent cognition, although I think they're all relevant. So I see challenges in 2 areas that have been mentioned already. And one is certainly relevant to all the talks we heard already, and that is, to put it into a bumper sticker, dealing with the data deluge. There's a huge amount of data already and more coming, and it is off-putting to people who aren't already comfortable with IT systems. I happen to be living with someone who's 86 years old. She's very intelligent, and I'm in an academic community. She reads constantly. She really doesn't use the computer at all. There is one there in the house, but I've been trying to figure out what kind of questions she might have that would be useful to answer using the computer. So far, the only thing I found that she really likes to do is print out her boarding pass before she goes to the airport. But I'm hoping that I can get her interested in other aspects of the internet little by little. So there are a lot of people, and the map that Tom showed, I think you referenced, 25% or something are online. There's a lot of people out there who aren't online around the world who could benefit from access to data, and I think that's a big issue for this panel. The other piece that goes with this, that's already been mentioned, of course, is the sort of security and privacy, and I would roll into that ethical issues, which we haven't heard that word very much, but I think it goes part and parcel with the cyber, bio, social, and then wrapped around all of that are sort of ethical considerations. And I think to deal with all of this at any level, we need to bring the right people together, physically and or virtually. And of course, the tools are available more and more to do it virtually, although I think there's a lot to be said for personal contact. And so these are the challenges, and the actions that I'm going to focus on are really around this exchange of information through people aspect. And I'm going to make some suggestions that I think NITRD or NITRD, I come from inside the Beltway, so I say NITRD, can use. One is to incentivize interaction among physical sciences and social sciences and life sciences. And in my experience, I think that, and probably NITRD and the Nanotechnology Initiative have made a difference in driving university communities towards more multidisciplinary research. I think the requirement for certain proposals to include multiple departments and people at multiple universities has really had an impact. That's my point of view. I haven't been at the university side of things. I'd be interested in your perspective. And so I think that the requirements for proposals by the NITRD agencies can incentivize that. And this ethical piece, which we have some experience in that in the Human Genome Project, there are people who think it didn't work so well, there are people who think it didn't work so well, but it was still important to do, is something to also be discussed, I think, among the NITRD agencies. NSF has this broader impact component of its proposals, and I would ask, is there a way to use that to drive towards what the goals of NITRD are, to engage more people, to make sure the results of the research are getting pushed out in meaningful ways? I think NSF might think about how to do that. And other agencies, if they don't use that aspect of their proposal review, might think about including it. I think that there's a need to facilitate interaction among academia and industry, and I come now from the Semiconductor Research Corporation, which is an industry consortium, takes money from its members, the semiconductor manufacturers, invested in a broad portfolio of university research that is driven towards the needs of the industry. So it's like a mini NSF. We put out calls for proposals. The people who review the proposals are from industry. I think that the NSF model has become more and more sort of internal, the academic community reviewing itself, and to the extent that it can engage non-academic experts more, I think it would be very healthy for the programs. And I know that's hard. SRC helps NSF to get industry people involved, and so if there are organizations like SRC, I mean not exactly, but some kind of consortia and industry bodies that could help bring the industry perspective into the program review, I think that would be very good. There's another report, we've heard a lot about the PCAST report, and I have to say, no good deed goes unpunished. I probably had something to do with the recommendation in the PCAST report that said there should be a strategic plan done, and then I got asked to be here today. There's another PCAST report that just came out this fall called University Private Sector Research Partnerships in the Innovation Ecosystem. And so this is really talking about how to bring industry in as a bigger player in the university research enterprise, and it has some useful information and examples that might also scale, so I encourage you to take a look at that. I second Mark's comment earlier about co-ops. I think that SRC is like NSF, but it's different in some key ways. And one of the ways that it is different, and I'll dare to say better in its own little way, is that the students that are funded under our grants, they're actually contracts, but essentially our equivalent of an NSF grant, all have meaningful interaction with industry experts during the course of their research, because they're doing research that our members want to see done. And so industry experts come into the university and meet with the students, ask them about what they're doing, give them feedback. The faculty appreciate it, the students appreciate it very much. In the end, of course, many of them go to work for our members, so it's sort of, that's why our members are involved, frankly. They get the benefit of all of this in the form of human talent. We have to actually, in the past, when the economy was better, and hopefully again in the future, we had to ration the number of our students who each member could hire. They fought over them. One of our members said once that we save $100,000 in the first year if we hire an SRC student because they are so far up the curve, so our training is cut way back in the first year. So there's a lot of benefit in the education process by having industry involved. And so to the extent that NITRD can think of ways to do that, if there are consortia, and frankly the IT industry does consortia all the time for standards development and other purposes. So you're familiar with the consortium model, maybe not for funding research, but in other purposes, and so I think those can be leveraged. Given the downturn in the economy, there certainly are experts who may have more time to provide input to the academic enterprise. And I've thought about this a little bit. You don't want to incentivize companies to lay people off because somebody else is going to pick them up. But maybe NSF could have a program whereby someone who is at a company, who stays at a company, can get support for a visiting scholar program for a period of time back at a university to build these bridges. And most of the information and people flow goes from academia to industry, of course, but to the extent that it could become more two-way, I think it would be beneficial for both sides. So those are sort of the points that I wanted to make. I think I'm well under my 10 minutes. Got us back on schedule, but I'd be happy to answer some questions. So I'm going to start over here, and then I'll come to Maria.
Celia, I'll echo your experience with a consortium kind of model because I've been running one for 11 years, and we've produced a lot of good students. They've worked on research projects. We've had a lot of interaction with industry. The problem that we have there is in times like now with the economic conditions, industry is pulling back, and they are not able to provide the support that they'd like to. Moral support, yes, but not financial support. What makes the center that I run work particularly well is that we use the sponsorship from the companies not to fund research projects, because we can go to the funding agencies for that, or we can get contracts from the companies. But we use the money for value-added kinds of things, bringing in speakers, for example, augmenting with equipment, providing bridge funding sometimes when that's necessary, travel for scholars. The difficulty is that no federal agency provides money like that for an organization to spend in a semi-discretionary way. And I don't know whether that's allowable under current rules, and I also don't know whether that's desirable. But from the standpoint of someone who runs a center and uses that money effectively, it sure would be nice if there was a way to get that from one or more of the NITRD agencies.
Good point. I agree. There are gaps, and there are ways to fill those. And NSF does have amounts of money. Well, NSF can't answer these questions, or maybe they can. There are certainly funds for things like running workshops and so on, so there may be types of money that are available. Maria.
I wanted to make a comment related to your experience and also what Mark suggested about students having internships with industry. And I just want to point out that there is a form of education that is vastly missing in the United States that is extraordinarily common in Canada, and I have yet to understand why it has not been adopted here, and that's co-op programs. So the basic idea is you do a 4-year bachelor's degree in 5 years, and you have usually about 20 months of working in industry. Every Canadian university has co-op programs. Many of them have them for students in every discipline, including arts and humanities. Apparently, I mean, I've asked about this here, and I've been told, well, co-op programs were sort of something that, places like Northeastern and other sort of vocational, and that's a bad word in the U.S., institutions instituted, and therefore no, really educational institution will put them in place. I really think we ought to do them. There's all kinds of reasons. One is it does help with women and minorities, because if you do a co-op work term starting halfway through your sophomore year, you suddenly see that the things you've been learning in classes actually matter in the real world, and so there's a validation for that. It helps affordability of college because you get paid for this. It helps employers because, again, to a very large extent, they hire the people that they do this. It's not that expensive to put in place. So I would like to lobby for people taking a look at this and doing it.
Thanks. Co-op programs certainly are common in engineering schools in this country, less so in other schools, or maybe not computer science engineering, but...
Yes, Philia Macedon again. I totally agree with Maria, and I just want to say there are some, I don't know what to call them, issues. I'm in an engineering school now, and when I told my dean about establishing a co-op, his response was, but we already have co-ops. But these are not part of a regular curriculum. They are, whoever is a good student, the company grabs them, and they get the co-op. So it needs the cooperation of industry, because otherwise these students graduate and the best get a job with industry, and so you can't enforce a 5-year program.
Yeah,
and that
there are a small number, and they work very well. And the graduating without a student debt, I think that would be very appealing to many, I think, involved.
I wanted to comment also on the co-op.
Is that mic on?
Maybe dead.
That's the deadest mic.
Now it is. Yep. It's a delay. Ray Vaughn, Mississippi State University. We have an accredited co-op program, have had for years. It's a 3-semester program that you must go through. Otherwise, you're an intern. But if you go through the co-op program, you're 3 semesters. Our best students are co-ops. Over 60% of our undergraduates have co-op experience through that program. We have students working at Google. We have students at Microsoft and other such places. A lot of cooperation from industry to the point where after those students spend about 2 semesters with a company, I've even seen them, most recently my Google student, turn down a full ride scholarship because he didn't want to screw up his job opportunity at Google when he finished. So I think there are some success stories out there, but I did want to comment on barriers with industry, and we do a lot of work with industry. There are some that we really haven't talked about. It's pretty easy to work with a national lab, and it's very easy to work with the government in a research capacity. Working with industry is a lot harder. You run into non-disclosure agreements, you run into adjudication agreements, you run into indemnification agreements, and you run into a lot of legalese that prohibits us, especially as a state institution, from doing work with industry. You also run into the problem of wanting to vet any publication that comes out of the research side, which is important to an academic and not so important to industry sometimes. You run into problems of intellectual property, that's been mentioned, and you run into problems of concerns over market share and not publishing anything that might reflect negatively on the company. So there are those kind of barriers that need to be addressed, and there really aren't a lot of programs out there to help us bridge that gap. That having been said, we're real supporters of working with industry. It's just a very hard thing to do.
Well, I hope most universities and most industries think it's worth the trouble, and maybe we should postpone the rest of that discussion because it's a big issue in and of itself. If we think it's related to emergent cognition sufficiently, I think it's broadly important. We can pick it up after the break. So I will turn it over to Ernest. Thanks. Thank you, everybody.
Thank you very much. Thank you for getting us almost back on time.
So actually 2 points of clarifications. The first one is NSF does fund a lot of the programs that you alluded to. IGERT is one of them. I'm sorry, GOLI is one of them. IGERT is another one. And there's other programs that actually encourage this collaboration between industry and academia. I mean, maybe we don't do a good job in trying to basically bring awareness to this program, especially from the industry side. But NSF has been doing a lot of work to push toward these directions, and we fund a lot of whenever we get our hands on in terms of these projects. That's the first thing. And the other thing, we also fund collaboration by providing funds for researchers to go and then do work with industry as well. And we allow that for, as you know, and sometimes we actually fund people from industry to come to NSF and then do work with academia. So I'm just trying to point this out because there are some mechanisms in NSF that will enable some of the things you just talked about.
Thank
you.
Those are great examples.
Thank you very much. We're going to take a break now.